Alrighty then. So this is going to be section 5.6, which we're going to call applications of the natural exponential function. Okay on blurriness. Okay, applications of the natural exponential function. Okay, but before we get to those applications, we're going to spend a little bit of time developing why the situations that we're about to look at can be appropriately modeled by the natural exponential function. And in order to get there, we're actually going to go way back to probably pre-algebra for most of us, and the idea of two quantities that are directly proportional. So if we say that two things are directly proportional, when one changes, so does the other in equal proportion. And so we have this kind of default generic way of representing two quantities which are directly proportional. We say that y is equal to k times x, where y is one of our quantities, x is the other quantity, and k is our so-called constant of proportionality. Okay? And the reason that we care about directly proportional quantities as it concerns the natural exponential function is, suppose we want to consider a quantity whose rate of change, either as a growth or a decay. Let's suppose that the rate of change actually depends upon how much we have of that thing at a given time. Okay, which we can think of tons of situations in the real world that model this. The most obvious one being the thing that is forcing us to interact in this way, which is the spread of disease. That bacteria or viruses will spread more rapidly as there is more of the virus or bacteria in existence. Okay, so the rate of change is actually dependent or proportional to the amount of the thing in existence. Money is another good example. Okay, as money compounds, the more money you have, the more interest you earn. Okay, and so we have a sense that there are very real world examples where the rate of something changing depends directly upon how much of that thing we have. Okay, and so tying this back into this pre-algebra concept of one quantity equals another quantity times this constant of proportionality, let's assume we have one of those quantities whose rate of change is dependent upon the current amount of the thing we have. With two very simple substitutions, we can tweak this basic generic proportionality statement to express what we're trying to show. That our first quantity, the rate of change of some thing, well, rate of change in calculus land should make you think derivative. So we're going to write the left side of this as dy dx. We're going to leave the k alone, the constant of proportionality. But now the second quantity is this first quantity's, the thing's, this rate of change of that quantity. And so the first, or the second quantity is just y. Okay? how y is changing depends upon the amount of y that we have and this constant proportionality. The rate of change is directly proportional to the amount that we currently have. So all I did was sub those two things. Okay, so this is an expression, or actually an equation, of two directly proportional quantities. dy dx and y are directly proportional, linked by this constant k. Okay, so dy dx is equal to k times y. And this is a representation of a quantity whose rate of change depends upon what the quantity is. Well, this right here is a differential equation. I know it's been a while, but we can actually separate it out and do some magic. Okay, so instead of writing it as dy dx equals k times y, and actually I'm going to do just the briefest little fix here. Instead of having this in terms of x, because so often with the problems we're dealing with time, we're just going to call it dt. So dy dt, the change in y with respect to time as opposed to x. It doesn't really matter, but just to keep it consistent. Okay, so we can separate this differential equation like so. We can bring the dt over here, so dy is equal to k times y times dt. Then we want to get our dy and our y together, so we'll pull the y over with division and end up with 1 over y dy is equal to k dt. And now we can integrate on both sides to figure out what the heck is this function y going to be whose rate of change is dependent upon the actual function, okay, and the actual value of the function. And so integrating on both sides, we have successfully separated our variables. Well, thankfully we just spent some time with the natural log and the functions that lead to it. So this integral, if we remember, leads to the ln, the natural log of y, sorry, the natural log of the absolute value of y. Gotta make sure that's a positive number. Over here, k is just some constant, not related to t, and so this turns into k times t plus, call it c prime. See why in a second, because we'll have an all-encompassing c in a minute, and so this is kind of just a placeholder. Okay. You could have done a plus c over here, but then it would have just kind of been swallowed up by the constant over here. The constant of integration to be different from the constant of proportionality, which is k. Got to keep that clear. Okay, so where is this leading? Well, we want to come up with a rule for y, but y is currently trapped inside of this ln, but we have a pretty foolproof way of getting things out of the ln, and that is with its inverse, the natural exponential function. And so we can pull this kind of crazy move where we're going to make both sides of our equation the exponents on e. We're going to kind of do an e to the on both sides. An e to the on both sides. So now these guys are living in exponent land. On this side, it has the effect of making the inverse magic happen, and what's left is just y. On the right side, we can now, if we so choose, write this as a product namely e to the kt times e to the c prime I guess this should still technically be in absolute values, but in a second we'll see, well, it's not possible for e to the expression to be negative, so we can actually do away with the absolute value, because this product here, sorry, this is the product, e to the kt times e to the c prime, it's got to be positive for forever and all time. And so we have this expression now, this equation, that y is equal to e to the c prime times e to the kt but this is just going to be some constant, and specifically what this constant is going to be can be found if we let t equal 0. Okay, but first we're going to replace e to the c prime, we'll just call it big C now. So c times e to the kt and letting t equals 0, we have y naught is equal to c times e to the k times 0. E to the k times 0 is e to the 0, meaning the 0 power is of course 1. And so y naught is exactly equal to c. And so we arrive at this general form of this function that if we have some quantity whose rate of change is directly proportional to the amount of quantity that we have, that will be governed by the function y equals some initial amount, y naught, times e raised to the k times t, where t is some given amount of time and k is some constant of proportionality. Okay? This should be familiar. We should have hopefully worked with functions like this in Algebra 2 and Pre-Calc, but now we can kind of see the genesis from calculus of where this relationship comes from. And just this thing right here should have kind of ticked in your minds that we might be looking at the natural exponential function, because we know that the natural exponential function has this remarkable quality that its derivative is itself times something else. Okay? And so this relationship here makes perfect sense in light of where we ended up. Okay? So the derivative, or the rate of change, is directly proportional to the function itself, to how much of this thing we have at a given time. Okay? And so the book, as it is wont to do, puts this into a theorem, which it calls 5.6.1. And all it says is basically what we did up here, that if we know that we've got some function y it further stipulates that y has to be greater than 0. For all t greater than or equal to 0, which shouldn't be much of an issue for the problems we're going to look at, because they deal with real quantities. A population, an amount of money, which I suppose could be negative, but in terms of the growth of money. So the function itself needs to be positive whenever t is positive. And if we have this other starting condition, that the rate of change of this function or of this quantity has this directly proportional quality to it. And that the rate of change, the derivative, is directly proportional to the function itself, where k is a constant and y equals y naught when t equals 0, then we can know for certain that this function y will look like y naught times e to the kt. Okay. So a little bit of a long-winded introduction, but I think important to see where this relationship comes from and why it does govern so many real-world growth or decay relationships. It's because those relationships, whether growth or decay, have this quality of having a rate of change that is directly proportional to the function itself. Okay? And only now through calculus can we kind of see that development of directly proportional leads to the natural exponential function. Okay? So now all we're going to do is look at 3 examples: 2 growth, 1 decay, and put this into play a little bit. So that'll start with example 1. Flip to a new page. So example 1 reads, in a certain culture, the rate of growth of bacteria is proportional to the amount present. Ooh, big words. That's important. The rate of growth, the derivative, is proportional. We are in this situation. Initially, at time 0, 1,000 bacteria are present, and the amount doubles in 12 minutes. If y bacteria are present at t minutes, express y as a function of t. You betcha. On a graphics calculator, we'll skip that, but they want us to estimate how long it'll take to get to 10,000 bacteria. Confirm analytically, that's what we'll do. So with all these problems, I would recommend starting with a t-chart, modeling the growth or decay of the particular quantity in question. Here you have t and y, where y is your quantity. For this situation, we know at time 0, we've got 1,000 bacteria. The doubling thing means after 12 minutes, if we've doubled and we started with 1,000, then we're at 2,000. With these 2 initial conditions, we'll be able to determine the function and then use that function to answer the question, which is, what was the question? How long until 10,000? How long until 10,000? Okay, so let's start with figuring out what the function is. Because we're told that the growth rate is directly proportional, in other words, that dy dt is directly proportional to y, we know that the function is going to look like y equals y naught times e raised to the k times t. So our job is to find out y naught and k for this specific function. Well, y naught is simple enough. It's when t equals 0. And so y is equal to 1,000 times e raised to the kt. And so really our job boils down to figuring out what the heck is k. Well, if they hadn't given us this second time snap, we'd be in a bit of a pickle. But because they have, we can use this information to figure out k. Because we know that at 12 minutes, at t equals 12, our function has a value of 2,000. So in other words, we know that 2,000 must equal 1,000 e to the k times 12. Just plugged in these conditions. At time 12, whatever this constant is, we should have 2,000 of those little bacteria. If we divide both sides by 1,000, we end up with e raised to the 12 times k is equal to 2. Then we're going to ln both sides. Ln both sides. Linning this side, we're going to drop that down. Ln of e is just 1. So we get that 12k is equal to the natural log of 2. And so k is equal to the natural log of 2 divided by 12. And we're in business. Now, coming back to our function, we have that y is equal to 1,000 times e. We just spent that time to figure out what k is. So e raised to the ln of 2 divided by 12 times t. And there's nothing objectively wrong with this representation, but it does get a bit clunky, especially if we try to go evaluate it on our calculator. And so there's a bit of creative algebra we can do to make this look a little bit nicer. And the creative algebra we're going to do is separating this exponent out a little bit and then seeing if something nice is going to happen. And the answer is yeah. And so the separation we're going to do is we're going to pull this 12 out. So we're going to make this into y equals 1,000 times e raised to the ln of 2 times t divided by 12. Okay? All I did was pull that 1/12 out. No big deal. Then if we remember our laws of exponents, multiplying exponents means that we've raised one exponent to the other. So we can rewrite this as y equals 1,000 times e raised to the ln of 2 to the t divided by 12. Okay? Multiplying exponents is kind of a reversal of the product property of exponents. Sorry, the power property of exponents. Raising one to the other results in multiplication. Why do we do this? Because now we have e to the ln of something. Well, e to the ln of something we know is just that something. And so this function has a much nicer form that looks like y equals 1,000 times e to the ln of 2 is exactly 2, but it's still being raised to the t divided by 12. And this is a much nicer function to handle and to evaluate and to plug into our calculator. Just doing a little bit of rearranging. And so now, when they ask us something like, when will we have 10,000, we can handle that. So we want to know, so that was all part A. That was all part A. We're going to skip part B, just go straight to the analytical. Part B asks, when does population, or when does y reach 10,000? Okay. In other words, we need to solve the equation 10,000 equals 1,000 times 2 raised to the t divided by 12. Alright. Our immediate first step is to divide both sides by 1,000. We'll bring that 2t over to the left side. We have 2 to the t divided by 12 equals 10. Divide both sides by 1,000. Well, the thing we're trying to solve for is up in an exponent. And so our math reaction should be, let's hit both sides with a ln and see if we can bring it down. So, linning both sides. Now we'll be able to pop down this exponent and say that t divided by 12 times the ln of 2 is equal to the ln of 10. And so then dividing by ln of 2, multiplying by 12, the time it takes to get to 10,000 of these bacteria should be 12 times the natural log of 10 divided by the natural log of 2, which comes out to be 39.9 minutes. So the actual math part of this is probably algebra 2. Algebra 2 is when you should have first learned how to do this trick where we're solving for an unknown inside of an exponent. That was when the magic of the logarithmic function first started to crystallize in our minds. We were actually able to solve for that exponent. Okay, so that was example 1. Normally here I would pause for questions, but it doesn't seem to be on the table today. So we will keep on trucking to example 2, which will be another growth problem. Example 2. Okay, what does example 2 have in store? The rate of increase of the population of a certain city is proportional. Oh, big word. Is proportional to the population. That means we're in this land. That means we're in natural exponential function land. Good. Okay, what are the specifics of this exponential growth? Well, in 1950, the population was 50,000, and in 1980, it was 75,000. If y is the population t years since 1950, express y as a function of t, which means that 1950 will be times 0, and then we want to predict what will the population be in 2010. Okay, well, let's set up our t-chart. We've got t, we've got y. In 1950, which was times 0, we had 50,000 people. In 1980, which on this timeline is 30 years after, times 30, we had 75,000. And we want to know in 2010 an additional 30 years down the line, so times 60, what will the population of that city be? I don't know, but let's find out. So the rate of change directly proportional to the population piece told us that the following is true. dy dt is equal to k times y, which means that our function, in this case the population of our city, will be governed by the function y equals y naught e to the k times t, so with a specific y naught of 50,000. And so again, our task is to find what k is, do that magic we did up here, and arrive at a function that we can manipulate. So off to the side, we'll deal with our second boundary condition, that after 30 years we're at 75,000. In other words, 75,000 is equal to 50,000 times e to the 30k. After 30 years, our population is 75,000. So e to the 30k then will be 75,000 divided by 50,000, which is 1.5. Hitting both sides with the ln so that we can bring down that exponent and solve for k. We get that 30k is equal to the ln of 1.5, and that k is equal to the ln of 1.5 divided by 30. Okay, same process as above. And just like above, we're going to initially substitute this quotient in for k, but then we're going to do some rearranging that allows us to write it in a slightly nicer fashion. But first we are going to do just a straight substitution, that our function should be 50,000 e to the ln of 1.5. Oh, a little small there. Ln of 1.5 divided by 30 times t. But again, that's a little clumsy, a little messy. We're going to pull that 30 out. And write this as e to the ln of 1.5 to the t divided by 30. I did sort of two things at once that I did in 2 steps before, but now this is the second time, so I'm just doing it in 1 step. I pulled out the 1/30th, and then I rewrote this as a power to a power, because that's what the property of exponents allows us to do. When we're multiplying powers, it really means taking one to the other. And then we get to apply this inverse property of the natural exponential and the natural log, and say that e to the ln of anything is that anything. So e to the ln of 1.5 has to be 1.5. And so the nicer version of our function is going to be 50,000 times 1.5 to the t divided by 30, which I think we'll agree is much nicer looking than that. So we're just converting it to a slightly nicer form. And this will certainly be nicer to work with when we're trying to figure out what is our population at 60. Okay? So we'll do that. If we call this, I guess I don't really need to pause, because if you need to catch up, you can just press pause on the video, but old habits. So here's A. The second part is answering the question, how big is that population after 60 years? What is y when t equals 60? Well, using our newly discovered function, that our population is equal to 50,000 times oh, that's not correct, times 1.5 raised to the t divided by 30. All we're going to do is plug in 60 for t, and we're home free. So y is equal to 50,000 times 1.5. If t is 60, then we divide it by 3. We're just squaring that. And so we get that y, our population, in 2010 will be 112,500. Alrighty then, that wasn't so bad. Okay, so the first two examples have been growth problems, where our population is growing, where our constant of proportionality is greater than 1. But our third and final example, we'll look at what happens when this number is less than 1, which will tell us that we are shrinking in size. Okay. Places this might happen in the real world, chemistry, yeah, isotopes, that's kind of the tried and true. Half-life. So, that's what our example is going to be. Example 3. What does example 3? Let's do. The rate of decay of radium, oh, rate of decay, that's different, not a growth, of radium is proportional to the amount present at any time, but it still has that magic property that the way it's decaying is proportional to the amount present at any time, so that's good. The half-life of radium is 1,690 years, and 20 milligrams of radium are present now. Half-life. Oh, look at that. They define it. Half-life of a substance is the time for half of it to decay. I think we can handle that. So our initial quantity will be 20 milligrams, and we're going to figure out the function that governs the decay, and we're also going to estimate how much radium will be present in 1,000 years. Okay, let's do it. So, as with our growth problems, we're going to start with a t-chart, comparing time elapsed to quantity present. Our initial quantity at time 0 is 20 milligrams. We're told the half-life is 1,690 years. So at time 1,690 years, half of the quantity remains, which to me means 10. And the question we're going to be looking at is, okay, what about at 1,000 years? How much is left then? Well, certainly needs to be more than 10 because we haven't reached the half-life, but we'll find out exactly how much. So, we heard the magic words in the problem setup that the rate of decay was proportional to the amount present. So the rate of decay, the derivative, rate of change, dy dt, is equal to k times y. Sorry, it's a funky looking y. Which means that the quantity present at any time will be governed by the relationship y equals y naught times e raised to the k times t. seen this story before. The only difference is now this k has got to be less than 1. Okay. So we'll go through the same process. We'll plug in our y naught, in this case 20. And go about trying to figure out what the heck is k. Well, the other condition we have tells us that after 1,690 years, half of the original sample remains. So 10 is equal to 20 e to the 1,690 t. Same setup as before. Dividing both sides by 20, get that e to the 1,690 t is equal to 1/2. Our unknown is an exponent, so we need to bring it down. Hit both sides with the natural log. So we get that 1,690t is equal to the natural log of 1/2. Oh, that's a mistake. I assume at some point, if we had been in the classroom, somebody would have yelled at me about the t that I keep using, as opposed to the k. But alas, we are not in the classroom, and so that mistake has made it 3 lines. This should, of course, be k. T was 1,690. My bad. So k is the natural log of 1/2 divided by 1,690. And we're going to do the same exact thing as the first 2 examples. Directly substitute in k, but then make it look pretty. Make it look pretty before we interact with it. In other words, y is equal to 20 times e raised to the ln of 1/2 divided by 1,690 times t. And in this third one, just going straight to the punchline, we're going to pull out that 1 over 1,690, and then we're going to apply the inverse relationship of e and ln to get 1/2. And so this function is y equals 20 times times 1/2 20 times 1/2 of t divided by 1,690. All right. And so, if we wish to know how much we have after 1,000 years, just plug in 1,000 for t and see what we get. So part B asks, how much after 1,000 years? Plug in 1,000 for t. And then probably reach for your graphing calculator. Figure out that that evaluates to 13.27. Okay, which in the context of the problem makes sense, because if it took 1,600, almost 1,700 years to decrease by half, 1,000 is less than that half-life, so we should have more than half of our quantity after 1,000 years. All right, I think that just about does it. As you can see, it follows pretty similar strategy or pattern each time. If we hear those magic words that say that our rate of change is directly proportional to the quantity, this relationship here, it means that we are governed by this function here. And so long as we have two initial conditions, we can solve for what that constant of proportionality is, sub it back into this function here, and then usually make it look a little prettier with some algebra, and then solve for whatever they happen to be asking us, whether it's for a quantity or for a time to get to a specific quantity. Once we have this function, it's algebra 2 stuff. Okay? So hopefully the homework goes well, and have a wonderful day.